Hello, guys, and welcome back to week 3. And this week we have a lot to do. So we have today's class. We're going to cover assembly language fundamentals, and we're going to also have a test 1. And you have already the practice questions already posted in iCollege or at iCollege during the weekend. And I hope you're going to have some time to play with them. And part of the last practice questions, they're going to be from today's class and from lab 2 as well. So, lab 3 is going to be this week, and it's going to be mainly enforcing the concepts that we're going to be covering today. I'll be there during the office hours, just in case if you have more questions. Okay, so I will look at the agenda that we're gonna try to achieve today. So we're gonna look at the basic building blocks of Microsoft Assembler, and then we're gonna explain the mass and program elements, constants, variables, standards, format, numeric, strings, and so on and so forth. And we're gonna explain how the assembler, the linker, and the engine of the x86 work. Okay, and we're going to also look at the intrinsic data types. That's going to be a very important topic today. So we're going to talk about byte, word, double word, and so on and so forth in terms of size, terms of range, terms of space, okay, and terms of type as well. Type, it means sign and unsigned, okay? So let's see, I think we're going to mainly focus on those parts today. And if we get time, we're going to go to the 64-bit programming. Otherwise, we're going to finish it in the other class. All right. Okay. So this is something maybe you have already looked at in lab 2, and that is mainly the basic main program for assembly x86. And these are going to be like the main elements in this program. So this is when you're going to have the declarations. So you're going to say 386, and I would explain what 386 means. And you're also going to look at the model, flat, and standard call, stack. So this is like declaration. These are mainly telling about what type of program you have. This is a data declaration. This is optional if you need it, and this is your code. So we're going to explain them one by one, okay? So this is the code, and this is the way we kill the process, or we end the program. Okay, like exit in other languages. Okay, so these are the whole idea, or this is the main part of the entire program. If you notice, like you have the main, end, and you have end main. So this is the end of main function, and this is end of the entire program. Okay, so let's look at them one by one. So this is the .386. So this is going to say you are dealing with 32 program. Okay, you're not using 16-bit or 64 or 128. By using this module, if you take this one off, the assembler is going to go 64 by default, but we have to say .386. Okay, and this model flat, the way the memory is going to be managed by the operating system, we choose to make it a model flat. And the way functions or procedures are going to call each other, we're going to use the standard call. Okay, so that's what this model is all about. Okay, and the dot stack, every program in the .386 must have a stack, and this is the space of the stacks, and the unit here is a byte. So you have 4,000 bytes. Okay, and you know every 1024 is a kilobyte, so it seems that you have like around 4 kilobytes of stack. And that's when you're going to declare your local variables. So you might wonder, I don't have functions, I don't have local variables, why do I need stack? You have a main, and remember, main is a function. And by default, main is going to use its own internal local variables that you don't see for when it communicates with the operating system. So we need the dot stack. Okay, we're going to compare this with the 64-bit program. Okay, a 64-bit program. All right, and then now we're going to have the exit process. So this is the way you're going to kill the program. So the way you kill the process, or you end the program, it is going to be a prototype. Okay, and this is the return value. When you kill the process, you're gonna have a return value of size D word. And D word means what? 4 bytes. Okay, so this is the exit process. All right, so here when you say invoke exit process, you are calling this class or this object. And this object is of a type proto. And it has like, it has a reference inside that is a D word. If the process ends normally, it's gonna return 0, otherwise it's gonna return the code. It's gonna tell you why the program was terminated abnormally. Okay, and this is the code. That is the most important part, the code and the data for us. And this is the directives. So these are all directives, okay? .386.model, .stack, .code. These are directives, and I would explain the difference between a directive and an instruction. So a directive is not an instruction. What do I mean by that? It's not going to be part of the executable. Okay, these are instruction, move, add, these are instructions. Okay, all right, and invoke itself. All right, so this invoke itself is a directive, not an instruction. It's going to be translated. All right, so here's where the part of your code is going to go. .code, and you are saying main proc. So that is the function name, which is main, and the type of this function procedure. That's what the proc stands for. Okay, and these are going to be the main function. It identifies the entry point. So if you load your executable in the memory, we know that we have segments, right, guys? By now, you should know that. So this is the .code, right? So when you go to the .code, the first instruction in this program, we're going to say move, right? So the main proc is going to tell the operating system that this is the entry point, and this is very important. All right. The reason I'm saying very important because I don't think so you have seen any program so far with Java or C or even in Python is going to be automatic, right? Without a main. And that is the main reason why, because the main is going to tell where this instruction is in the memory, and it does some other things as well. So if you can see, main is a program that starts here and ends there. So it's gonna take care of executing this. And when it executes this part of the code, it's gonna communicate with the operating system. So if you write your own function unable to do that. So the main is just more than just a function. It's a program. It's like the linker, the assembler, you know, the loader. Main is one of the utilities that most programming languages uses. Okay, and this is going to be the invoke. So this is the call. That's the idea of the standard call. So the way you kill the process or you end the program. So you might feel it's a little bit weird. I say kill the process. That is the terminology used in the operating system community. Okay, so the invoke right here is the standard call. So that's why we are using the standard call. Can we invoke or we kill the process in a different way? Yes, we're going to talk about that later. Okay. So we can actually use exit right away, like the way you guys use maybe in C. If you have done any programming in C, we say exit 0. And the reason we say 0, we are just passing a parameters, right? We're assuming that the application or the program is going to be ended normally. So this is a D word. So that's like returning this code right here. For you, you assume it here is going to be returned. Okay. And that is actually the end of the main and the end of the program. So if you want to write another procedure, it has to come in this part. If you write anything after this part, the compiler or the assembler is going to ignore it because that's outside of the program. So if you want to write another function, it has to be declared between the end of the main and before the end of the program as a whole. Okay, so these are the main components of a program. Okay. So this is what I was explaining right now is the .86 program. So that's the SM file. It's going to be an input to the assembler, and the assembler is going to produce an objective file. So it's going to organize this file in a way that's very close to the machine and something that the linker can understand. And if you are using something like invoke, we use invoke. So invoke is a function within the operating system. So the linker is going to get the code of the invoke and then is going to tie it or it's going to put it together with your code, the .asm code, and then it's going to produce the executable. Once you have the executable, you can load the file actually to the main memory right away and run it, or you can load it to the debugger. So that way you're going to execute it one instruction at a time. And that's what I'm going to do just in a second. Okay, so that is the whole idea of a debugger. Okay, so right now I will see if I can stop right here. Yeah, I will say discard. Okay, and then let me see if I can go and share. Where is the share part? Yes. And then I'm gonna share the, where is that? Okay, I need to share the Visual Studio. I already have it. So let me see if I can share it. Okay, so give me 1 second, please. It should show up right now, but I think I can go and okay, it seems there's a certain issue right here. This is the virtual machine. I hope you guys seeing it right now. So this is actually the Visual Studio main screen, and these are the things that I was talking about right now. So this is the main program right here, and this is the .data, and this is the .code. Okay, and first we need to actually call the assembler, right? So if you want to do this, you know, guys, what to do, right? So if you're going to go to the project and you say build the project. If you say build the project, that is, I already built it. So that is, you are passing this to the assembler, and the assembler is going to get the .object file, and then it's going to pass it to the linker, and the linker is going to produce the executable. So now you have an executable file. Okay. If you have the executable file, then now maybe you need to run this executable file, right? So you're going to go to this part, and let me say rebuild the project, so that way you will see how the assembler works. So that's how the assembler works. That's the .sm file. Do you see it right here? So it produces the .sm file, and the .sm file is going to be passed to the linker, and the linker is going to produce the executable file, if you see it in the bottom where I'm highlighting right here. Okay. So this is now your executable file, which is already in the hard disk. Now we need to run it, right? So we're just gonna go right here and run it. If we don't have this breakpoint, okay, the program is gonna run and is gonna disappear in no time because the microprocessor is really fast, correct? So if you wanna do this, we have to create a breakpoint. The way we create a breakpoint, you just come to the gray area and you create the breakpoint next to the instruction where you need the execution to stop. So we know that the microprocessor works in terms what? Fetch, decode, fetch, execute, right, guys? Okay, or fetch, decode, execute, or fetch, decode, fetch, execute, and store, right? If you want to stop this process, you have to create a breakpoint. Okay, so now we are creating a breakpoint right here, and we're gonna say stop right here. So when we say stop right here, this instruction is not going to be executed. The CPU is going to stop at the move. Once we say step over it, it's going to execute it and go to the next instruction. And the next instruction right here is exit. Okay, so if you want to look at that right now, let me just go ahead and say run the program. So when you run the program, as you might have seen that in the lab 2, so you have to show the registers, and that is when you need to go to the debug menu, right? And if you're gonna go to the debug menu, you're gonna go to the Windows right here, right? Let me go back. It's always hard. Okay, so you're gonna go to the Windows here, and then you're gonna choose what? You're gonna choose registers. If you use registers, it's gonna show you those registers on the right side. And you should also show the memory, and you should go and choose memory 1. So that's what you see in the box right here is the memory 1. Okay, so now I can see the registers, part of the CPU, and I can see the memory as well. Okay, so this is only doable when the program is running. So if your program is not running and you're trying to go to the window to activate the memory and the registers, you are not gonna do that. You'll not be able to do it because these are only available when you are in the running mode. So that node is already being posted in the lab 2, and I hope that you already learned that lesson. Okay, So let me go back right here. Now I want to know I have a memory, and this memory is declared as D word, and I have a value that's stored in that memory, hex value, 12. So you have 12, and you have AB, and you have 3, 4, and you have 5, 6, and you have H in there, right? So these are all values. It's a large value, and it has 1 byte, 2 byte, 3 byte, 4 bytes, because we know every 2 digits in hexadecimal, they represents a byte, okay? Because every digit represents 4 bits. So 2 bits, 2 4 bits are 8 bits. That's a byte. So this is 1 byte, 2 byte, 3 byte, and 4 byte. So if you want to search for A, where A is in the memory, okay? So this is what we want to do. So let me see, right click right here, and then I want to say 32-bit, forget about this one. I want to take this one off. Okay, and let me go to the byte integers. Okay, so I'm getting the byte integer right here. And then I would say ampersand sign, that is the ampersand if you can see it. And then I'm saying A. Okay, ampersand A, and then I press enter. You can see that this value is already here. So that's my memory. That is the address that I was talking about. Okay, that is the address of this variable, which is A. Okay, this is what we're gonna load in the address bus. Okay, so it's 0x. 0x means what? Means this address is being written in hexadecimal. And if you notice the size, it's 00, that's 1 byte, 40, that is 2 byte, 40, that is third byte, 00, that's the fourth byte. So fourth bytes means what? 4 by 4, 4 by 8 is going to be 32-bit. So the address bus is 32-bit. And that makes sense because our program is a 32-bit program already, right? The only thing that's weird, we are not seeing 12AB as the first, right? We are not seeing 12 and then AB and then 3, 4 and so on, okay? And this is what we actually call what? This is what we actually call, we call it Little-endian. So the data is going to be stored from right to left. So if you notice 5, 6 is first, 3, 4 is second, AB is third, and 12 is fifth, right? So 12 is at the end. So the memory goes from low, to high. It grows in this way. Okay, so this is very important. We need to understand that. All right, and this is when you look at this part, we're going to explain a lot of the slides. So I'm not going to explain them like in order, but I will talk about them right here. Okay, and if you look at the register right now, do you see this value, which is 12AB3456, already moved to the register? No, there is a garbage. These values are garbage, default values. We don't care. Okay, the assembler is gonna upload or is gonna assign those values randomly, and that is a decision made by Microsoft. They're not assigning them 0, they're assigning them random values. Okay, so the bottom line here, you can see the breakpoint. If you have the breakpoint at the move, that means this instruction is not executed yet. So how are we going to execute it? If you look at the signs right here, you're going to have the step over. This is what you're going to focus on right now. So if we say step over, then the register EAX is going to have what? 12 AB 3456. Are we going to have them left to right or left to right or right to left? We know registers, they start from here, right? The low, this is the H, and then this is the AL, and then the AH, and then we're gonna move on right to left, right? So if we're gonna take 5, 6 from here, this is very, very, very important. So the 5, 6 is gonna be stored, is gonna overwrite CC. And then 3, 4 is gonna overwrite FF. And AB is gonna overwrite 19. And 12 is gonna override 0, 0. You see it? So this is, in this way, we're gonna have them in the normal way. 1, 2, A, B, 3, 4, 5, 6. So that's why we have a Little-endian in here, okay? So let's do that. Let's say step over. And if we do it, that's what you're gonna see. 1, 2, A, B, 3, 4, 5, 6. So it moves it, and if you see the pointer right here, it moves to the next instruction. All right, so in this next instruction right here, it's waiting for you to say step over. So fetch, decode, execute is waiting now. If you say step over, it's gonna fetch, decode, execute right away. Okay, and I can tell that the fetch and decode has already been taken place.
That is the way microprocessor is designed, especially x86. All it waits for now is you telling it, go and execute it. It's not gonna waste the time for fetch and decode. It does that in no time. Okay, so this is actually the basic idea. So this is the variable name. This is the data type, D word. We're gonna talk about different data types as well. You can have a byte, you can have a word, and you can have a D word. D word means like what? 4 bytes. Okay, so this is the basic environment, and this is your main memory. Okay, and this is, these are the registers. Okay, so if we wanna, let me see what I can do. So if we want to talk about like killing the process, we're going to just say stop debugging, right? So that's going to kill the process. We're going to go back to the editing mode. So if this is my AD word, I can say also B. We can have it as a word, and we can store 1, 2, 3, 4. That's a hexadecimal. And we know it's Little-endian, so it's going to store 3, 4 first, and then 1, 2 in the memory. Okay? And then we're going to have a byte, okay? So you're going to have A, B. C is a keyword. You will see that. If I say C byte, and then I'm just going to store 1, 2 as a hexadecimal, or let me make it unique, 7, 8 as a hexadecimal. You can declare a decimal as well. If you take this H away, this descriptive, then the 78 is going to be treated as a decimal number by default. If I want this to be stored in a different format, like hexadecimal, decimals, binary, or octal, all I need to do just add O. So that's going to be stored in octal. If you want to store it in binary right away, you're going to say 1. So it's 7, right? So you're going to say 0, right? 1, 1, 1, that is 7. And then we have 8, 1, 0, 0, 0, right? And then we're going to say store this as a binary. So this is not going to be read as, I don't know, 11,000, whatever. So now this is going to be read as a binary. Okay? So you have to just assign this part. Okay? You have to assign the descriptive right here. But you're going to have an error. The assembler is going to say C is a keyword. Okay? So if we try to go to the build, that's what I like to do all the time, to produce the executable first and then go and run it. So if I say build the project, I'm expecting an error. You will see it. So say it failed if you see it right here. Okay, and it says syntax error, and it gives you right here syntax error C. You see what I'm talking about? So C is an error. So you might, it drives you crazy. At least it did when I once was playing with it, because the last thing I can think about that C is something that's not acceptable. So if I say C1, so that's not a keyword anymore, and I say build the project, then you will see that everything works fine, you see? So now I can run it again. So if I run this program again, I still have moving this. I can say actually play with the other registers, move to BL or BX, right? Because we have a word. Move to BXB, and we're gonna say move to CL C1. CL is 1 byte. So this is 32-bit, EAX, this is BX. So that's like 16-bit, and this is CL, and that is the low. I can say CH as well, either one of them, okay? So let's see, we're gonna stop the execution right here. Remember, when we have the breakpoint, the execution is gonna stop right there, okay? So let's run this program now. You're gonna see the same thing, the way I arrange the memory and the registers, and this way you can arrange them in any way you want. Okay, so if you're gonna do the same thing, you're just gonna say ampersand again, and then you're gonna say A, and this is gonna take you to the values, right? So you first have 5, 6, 3, 4, A, B, 1, 2. It's gonna be in a Little-endian, and that's what you see, 5, 6, 3, 4, A, B, 1, 2. And then this is also 2 bytes. If you have 2 bytes, then we have to go right to left. If it's 1 byte, no brainer, nothing to go either right to left or left to right. It's just gonna keep it there. So if you go to this 3, 4 is gonna be stored first. So that's 3, 4. And then after that, what? 1, 2. That is the B value. And then the C right here, C1, it's gonna be 7, 8. Do you see it? It was already stored in hexadecimal. That's how the system here is designed. But we were able to write it in what? In binary. So it was understood right away that this is 8, and this is what? And this is 7. It was 78. So this is 1 byte. You just put the byte as is. Okay. So now we have the we are moving A to EAX, right? So A is a D word. Okay. So that is unsigned byte. Keep that in mind. Word is unsigned. Sorry, this is unsigned 4 bytes. This is unsigned 2 bytes. This is unsigned 1 byte. What if I need to store something negative, right? Like a negative number, minus whatever. We're just gonna add an S right here. S, D word, S word, and S byte. So if I say declare assign variable, just have the size if it's a word and add S before that. I will show you that just in a second. But right now, let's just play with the step over right here. So we already moved AX. If we want to move B, which is 1, 2, 3, 4 to BX, this is the only register that's going to be affected because these are the 16 bits, right? These are the 2 bytes. This is a byte, this is the byte. So 0, 0, and 6, 0 is going to be overwritten, right? By 1, 2, 3, 4. Okay, the rest is not even seen by the assembler. So just see the BX. And you notice that, see it? It's 4, 3, 1, 2. The value right here remains as it was. For the CX, we only gonna change the spot 0, 5 because we are moving C1 to CL. So this value is gonna remain the same, okay? So it's gonna be 0, 0, 4, 0, 1, 0. Okay, so if you do that, then this is exactly what the case is. We're gonna say step over it right here, okay? And then this is what you saw. So we moved C1 to CL, and you see it right here, right? That is the 78. Which is we moved something from the memory, the 78 here. Okay, we moved it from the memory to the CL, and the rest remains the same. Okay, so this is basically the memory. And as I said, and this is how we move from memory to registers. We're gonna show you an example how to move from registers to a memory. Okay, and that is very, very important as well. And keep in mind, as I said, that your memory is flat. And you notice that, right? And every time we declare a memory, this is the first memory we declared, D word. And this is the word memory, right? It was next to it. Why that is the case? Because we say the model, the dot model, flat. So we choose the memory to be flat. And flat means what? Data is going to be in a sequence. It's going to be stored in a sequence. Isn't that the case all the time? No. Sometimes it's better to store the data in different orders to allow saving some time, because some algorithms, they access the memory faster when the data is not sequential, is not stored in a sequential way. Okay, and this is gonna be your 7A. So this is, and we know that this data being stored in a Little-endian. So that means we store things right to left. Okay, so this is another idea that you need to keep your eye on. And let me do the last thing. So let me now say I want to move something. Let me declare a memory right here. And let me say, let me just say D. And let's declare it as a D word. Okay. And since we say it's a sign, a negative number, we can say SD word, right? And then this SD word, I can declare, let's say, a negative value. Let's say we're going to say negative 12 in decimal. Okay, so how are you going to declare a negative value in hexadecimal? You can do that, right? In hexadecimal, if the number is greater than, let's say, greater than 7, if we say 8, 3, so that means 8, the most significant bit is going to be 1, so that's going to be a negative value without writing the sign. So it's going to be negative right away, okay? Because the most significant bit is going to be 1. So let's just do it with the decimal right now. And then let's have negative 12. Okay, so if this is the case, let's build the program. So every time you do something, you have to do it in this way, okay? Or let's say, I'm sorry, let's just say SD word and question mark. Just gonna declare a free memory, and then we're gonna assign it a value. So let's say now, say move to D negative 12. Let's assign it. So this is a question mark. Either you assign it a question mark, or if you want to assign it 0, that's fine. A question mark, it says it's a directive that's going to tell the assembler assign whatever the value is, and the assembler usually is going to assign a negative value. Okay, sorry, it's going to assign a 0 value. I'm sorry. All right, so if that is the case, then let's now go. Let me move this. I know you guys, you don't see it, but it is very important right here for me. So let's say go to the build and say build the project. So if I build the project right now, everything succeeded. So we are good to go. And then let's go and run it. Okay, so we're gonna see the same memory, okay, 7, 8. And then we have D, and remember these 4 bytes are gonna be for the D, right? 1, 2, 3, 4. Okay, so we're gonna execute everything as we did before. So we're gonna execute move A to EAX and move B to BX. So the only first 2 bytes, they're gonna be changed. You see it here, 1, 2, 3, 4. And then this 0, 5 is gonna be overwritten by 7, 8, and you will see that. Okay, so you can see it is 7, 8, overwrite the 0, 5. And then now we are moving negative 12. So negative 12, you should see it right here, but you will see it in a very weird way. Okay, and that's gonna go back to your binary skill. Okay, how good are you at converting numbers from binary to hex and so on and so forth. Okay, so if you're gonna say right here, so that is what you're gonna have, F4, FF, 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 and that's actually negative 12. And if you don't believe me, just write 12, okay? And then try to have this 12 2's complemented and write it in a 4-byte way, you will see it in this way. So it should be the other way around because this is Little-endian, right? So it should be FF, 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 and then F4. Okay, so the F4 is the most right, but it was stored as the most left, and that's the Little-endian. That's the way data is stored in the memory in x86. Okay, and I want to also get your attention to the general purpose register. We talked about ESI, it's there, EDI, it's there, instruction pointer. So the instruction pointer right here is at the exit, is pointing at the exit, and it is active right here. And this is the stack pointer. Okay, so and this is the base pointer. So if you take this value from the stack pointer and right click and you copy this value and you go to the address bar right here and you're gonna just base the value right here and you press enter, that is the stack memory. So you might say I did not use the stack, the main used it when it communicates with the operating system. Okay, so these are the general purpose register that we talked about in the theory part. So the instruction pointer all the time moves. By the way, you can take this arrow right here and you can move it to the back to the CL. Okay, so you can do that. All right, and you see like the instruction pointer is gonna point at the next instruction, which is move -12. Okay, so if you wanna do that, you will see like this value is gonna change. And you should know that this is 1C, and we will see by how much this value is gonna be changed, right? Okay, so it's 22 now. So if you subtract 1C from 22, it shows you how many bytes the instruction pointer actually jumped. That's the amount of memory in the dot code that's been jumped over. Okay, we're gonna talk about this in more details in the future, but this is like basically what I would like to share with you in terms of the basic assembly code. Okay, so let me see if I can go back now to my slides. Okay, and let me go to the share and let's see, where are my slides? So now I want to share. It's not what I would like to share, so you need to go away. And yeah, that's what I would like to share. Let's see if it is there. Yeah, so this is what I was talking about, the registers and everything, and I hope now you know what the registers are. The only thing that I didn't talk about is the flags. I will do that in more details later, but you can see it right here. This is the E flag register. If you right click and you say, I want to see the flags right here, it's going to show you the flags. Okay, so you already have done that in the lab, so I'm not going to spend a lot of time on this slide. And these are some standards. So when you write a code in assembly, it is going to be very handy and it's going to be very helpful if you could follow those standards. So capitalize nothing or capitalize everything. So stay consistent. Descriptive identifier names. Try not to say A, B. Try to give something meaningful. And I know you guys already know those in when you learned different languages, right? So same apply to assembly code. And these are other standards as well, okay? So try to look at them, please. And then when we talked about the program, just keep in mind, so we have instructions like move and add. These are instructions. We have memory locations. So this is going to be a memory location like the A, when we say it's a D word, okay? And we talked about B and so on. It is a word, right? So these are all memory location. Or we're going to have immediates like 5 and 6 right here. These are immediates. And the immediate operand, you know, so you need to keep that in mind. That is, the immediate is part of the instruction. So the question is the immediate sign or unsigned, because we know D word is unsigned, right? And then when we say D, if you remember, we say D S D word. So that is a sign, okay? And then we brought it as a question mark when we did that using the Visual Studio, right? So are the immediate sign or unsigned? Since they are part of the instructions, they are treated as assigned integers. And they have a limited range, then that depends on the size of the destination register, okay? So the 5 right here, when you move 5, I usually give this example. I say move to AL5, move to AX5, and we're going to say move to EAX5. Are these 5 all the same? No. 5 here is going to be of a range 8-bit. 5 here is going to be within the sign range of 16-bit. And 5 here is going to be of a range of sign 32-bit. Okay? So it's going to be 2 to the power 7, because 1 bit is going to be for the sign. This is 2 to the power 15, and this is 2 to the power 31. Okay? So that's the range of the immediate. And these are the registers we talked about, and this is like the main memory that I explained to you just right now. Okay, and we already explained the idea of a debugger and why we need a debugger. And you saw, like with the breakpoint, we stopped the execution and we kept saying step over, and every time we say a step over, we are running 1 instructions at a time. Okay, and then we played with this example. So this D word, as I said, it is a size of 32-bit, the D word. And it is like when you say integer A in Java, it's similar to it. It's a 32-bit. But remember, this is unsigned. In Java, integer means sign. So the right declaration of integer in Java in assembly, the other part is going to be SD word, because that is sign. Okay? So you have to declare, when you declare a variable like byte right here, you have to assign it 0, or you're going to say byte B, maybe you're going to say it's a word, you see a question mark, but you cannot leave it blank. This is not acceptable. You cannot say D is byte and you have it like without anything. Just leave it blank. That is not acceptable. Okay, so you have to initialize. That's a syntax. And I talked about this just right now. These are the data. You can declare it as a byte, word, D word, quad word, or double word. Or these are for all and sign. If you want to do this for sign, it's going to be S byte, S word. Just add S, okay? So if you add S right there, this is going to become a sign word, okay? So keep that in mind. These are the integer constants, and as I already explained that, right? So these are going to be your Redux character. It's going to be, if you say 15, by default is going to be treated decimal. If you want to be very specific, you can say 15D, okay? Or you can say 15 hexadecimal. These are 2 different things, right? And you can say it as a binary. I already explained that to you, right? So this is, sorry. So this is 1, and this is 5, right? You can do this and you write B right there. You can write it in octal, okay? So these are the ones you do it. If you say nothing, the assembler is going to treat it as decimal. Or you can say it in this way as well. So I already talked about this part. And these are very important. So the precedence, okay? So the precedence right here, the priority, the highest priority is for parentheses. And then you're gonna have unary. So when you say plus 5 minus 9, so this is a unary operator. So this has a priority more than the binary because this is a binary operator. So if it's -5, we have to, because you know, negative right here is a function that takes +5 and convert it to a negative number. Okay, positive is also a function that's always going to take 5, whatever that 5 is, and make sure that is a positive number. That's going to happen first, and then we're going to do the subtraction. And then we know multiplication and division, they have higher priority than addition and subtraction. And the modes, of course, you guys know it. So that is the level of precedence, all right? So if you have this part right here, so right here is gonna, by default, is gonna multiply first because multiplication comes before addition and subtraction. Keep in mind, this addition and subtraction is not binary operator, it's a unary, it's not a binary operator, okay? This is the same thing right here. So you have to do the mode, right? Because the mode has high priority than subtraction. Okay, do the mode 5 first, and then you're gonna do the subtraction and so on and so forth, okay? So keep that in mind, guys. And this example that is something I would like always to tell my students to do all the time. If you are not very sure, use parentheses. So when you use parentheses, you are enforcing the precedence. The only thing that might confuses you right here, if you look at the result, you say, why 3? That should be a fraction, but we are dealing with the integers. We don't care about the floating point. And that's what happened in Java. Even if in Java, if you say print out 5 divided by 2, by default, Java is going to give you what? 2. It's not going to give you 2.5. If you say just the dot right here in Java, Java is going to show you the 0.5 because it says that, okay, you're talking about floating point. But here we are not talking about, we don't have any dots, so the result is going to be 3 and a fraction. Since it's an integer division, we're going to ignore the fraction. Okay? And these are the quotations. So you're either going to have a single quotation or you're going to have a double quotation. Keep that in mind. Okay? The only special case, it's right here. All right? So this is the quotation, single quotation here and there. So about these. So these are going to be within, they're going to be treated as a normal ASCII. So the assembler only is going to consider this and this. And then when you print this one out, you're going to see those quotations in addition to whatever you have right here, right? You're going to see it. But you are not going to see those quotations in the outside. These are not going to be printed, right? Because these are only directives that's going to say whatever we have in there, it's a constant thing. How about the real numbers? That's what I was talking about. So we're going to deal with the floating point at the end of the semester. So I'm not going to waste the time with the floating point. We're focusing on integers. So when you use a variable, like remember when I said C and we said CD word, right? We got an error or it was a byte, whatever that thing is, okay? If you say C, C is a keyword, so it's an identifier. So we change it to C1 in order to make it work, right? So if you declare an identifiers or a variable name, make sure that it doesn't have any of those instruction mnemonics, register names, try to avoid those. Otherwise, you're going to get an error. Okay, and in the book, you have the list for everything. Okay, so these are the identifiers. So you can use those in assembly, by the way, but it's not recommended. You can declare your variables in this way, but I would advise not to use them just to avoid confusing the assembler. Okay, and I already talked about directives. Okay, so you have a lot of directives right here. So directives are not part of the Intel instruction set. And if that's the case, your executable file is not going to have directives because these are things that's going to direct the assembler in what to do. And when you write directives, keep in mind they are not sensitive. If you write it in this way or in this way or in that way, they are all equivalent. Okay? And as I said, there is a difference between an instruction move and a directive D word. And that is going to be part of the executable. This is not going to be part of the executable because this is only tells the assembler preserve a space of size what? 4 bytes. That's it. In our case, when we use the Visual Studio, it goes from left to right, right? So it goes like in a horizontal way, not a vertical way. I like the vertical way. Okay, so keep that in mind. Even when you have x86 and it's Intel, but the operating system is different, okay, or the operating system is the same, I'm sorry, and using a different directives, that's going to be a problem as well. Okay, so directives is, they might sometimes written in a different way. So in x86 Linux, okay, we are not going to say .code, we say .text. Okay, so we say .text. In x86 Windows, we say .code. So it's the same thing, but different directives. Okay, so the directives, even for the same operating system, I mean, for the same Intel hardware, they have different directives based on the operating system. Okay. And these are the ones that I have in here. These are all directives, dword, .code, main. These are all directives. These are the instructions. All right, so these are the ones that they have fetch, decode, and execute. Okay, they encoded, they are part of the instruction sets. Look at the appendix in the book, and you're gonna see all type of directives in there, okay? Already talked about this program. The only thing that I didn't mention is the labels, okay? So what is a label? Okay, a local variable here, A, is a label. This one, L1 in here, is a label. So what do you mean by this is a variable name? Yes, it's a label. So when you say A in here, the assembler is gonna go jump to this memory and say, what is A? You're gonna say it's dword and it has a 5. So right here, you say jump to L1. What is L1? We're gonna go in here, then we're gonna know, oh, this is a label. So this is maybe something you need to repeat, right? You're gonna repeat forever or repeat for multiple times, right? So this is a code label and this is a data label, okay? So you can have labels in case if you wanna go to. There is a well-known programming language, many of the programming language has this instruction, and it used to be very much heavily used, the go to, but nowadays is no longer because it makes testing harder. Okay, so an instruction contains, if you have an instruction like this one, move, has a label, right? Either like this label or A is a label as well. As the mnemonics is the move itself, it's the word itself. And then the operands, this is the operand EAX M5, these are operands. And then you can have comments. The way we write comments in assembly is semicolon. And we say move whatever. And I would heavily advise you to follow this style. Write the instruction and explain it. Because if you go back to your code a week from after you write the code, you're gonna be in trouble. You don't really know what you did quite some time ago. Okay, so you need to have that part as well. So I explained that in more details in the labels. This is what the label is, okay? And that's why we use the label. We're gonna talk about the labels when we're gonna move to the loop instructions and if statement, okay? We're gonna see how important labels are, especially the code label. Like when you wanna jump to the target. So you say, what is target? You go here and you figure it out. If it's a data, if you're dealing with a data label, that's exactly what we are doing, right? So we just go to the variable name. So these are all array, count, these are all labels, and you can refer to them within your own code. Okay, these are the mnemonics, like move. Mnemonics means instructions, add, sub, mul, jump, call, and so on and so forth. These are all instructions. We already know move and we already know add and sub. These are straightforward. We're gonna cover this very soon. All right, and these are the operands. So you need to keep that in mind. This is an operand, that's integer, literal, right? This is also an operand, so I can say this is correct. I can say move to AX 2 plus 4, okay? So what is gonna happen, first we're gonna add 2 to 4 is gonna be 6, and then we move it. So the question right now that I have for you, what is plus right here? Is it an instruction? No, it's not. If you say an instruction, it's not, it's a directive. So this is gonna be called as a directive, and then we're gonna call the program, which is later gonna have the instruction add. So this is not the instruction add. It's not the mnemonic add. This is a directive. So if you see an expression, you have to evaluate the expression first and then move it. So try not to be confused, please. Look at this part very carefully. These are registers and this is memory right away. So these are the operands. So the operands could be immediate as just give it the value or you give the expression. Okay, or it could be the register name or the memory name right away. And these are the immediates, okay? So we need to also, when we say add to AL5, and just imagine if we say move to AL6. So the destination right here is what? AL, and it has a 6. When we say add, we are adding 5 to AL. So AL no longer is 6, right? So it's going to be what? It's going to be 11. So that's going to be my destination. This is going to be my source. So this is the source. This is the destination. So keep that in mind, all right? So the instructions, some instructions, they have no operands. So we say set the carry flag, right? Did we say anything about the carry flag? Did we pass it as an operand? No. So that's no operand instruction. We talked about that in the big picture. We say increment EAX, how many operands we have in here? One operand, just a register, or one operand, it's just a memory right here. So the instruction itself, it requires only one operand. So this is unary, this is 0. This is binary, you're adding this to this. Remember, this is the source and this is the destination. This is also, you're adding immediate, right? Or subtracting immediate from the destination, which is a memory. And here you're gonna evaluate 36 by 25, you're gonna get a value, and then you're gonna add it to EAX. And when we learn mul instruction, we will see that it has 3 operands. So it's gonna mul 5 by EBX, and then it's gonna assign the result where? To EAX. Okay, so these are the operands and the instruction format. Okay, some of them 0, 1, 2, or 3 operands. Okay, and I already talked about the comments. You can, the single one is always semicolon, and then you write whatever you want. That's going to be a comment. But if you want to write another line and the new line, you have to say another semicolon and you write it down. But if you want to have multi-lines, okay, you're going to have multi-lines. This is for the single, easy. Here you're going to have comment, and then you're going to have the exclamation sign, and then you write whatever, multiple lines, and at the end, you're going to do it right there. In Java, you're doing the same thing, right? You're going to say \* and you keep writing, and at the end, you're going to close it in this way, right? This is the same thing. Instead of the \* and star, you're going to say comment and exclamation. If you don't like the exclamation, you can use the %, comment, and you can use the %. So either one. But remember, if you start with this, close with this. If you start with this, close with this. This is for multi-lines, okay? So hopefully by now you already know the basic elements of the assembly code. Okay, so and the data type, we already talked about the data type, right? So we have byte, S-byte, that's for the sign byte. Word, S-word, D-word, S-D-word. This is F-word, quad word, T-byte, real, so you don't need to focus about these. So focus on these parts right here, okay, up to this part. All right, these are very legacy data directives that used to be used quite some time ago, but they are no longer used, okay? So just keep that in mind. Right now, we're gonna focus on these. All right, so when I say 12 minus 12, and then we assign it to, let's say, A, and it is S-byte, okay? When you store this, you will see this in a different format. So 12 means what? We have 1, 2, 4, 8, right? So that is 12, right, guys? You with me? Am I right? And then the rest is going to be 0, 0, 0. So that is 12, but we need negative 12, right? So this is going to be 1, 1. We're going to flip, right? 1, 1, 1, 1. And then we're going to add 1, right? So 1 and a 1, 0 and a 1. 1 and a 1, 0 and a 1. This is 1, right? And then 0, and then 1, 2, 3, 4. So if you look at this part, this is 4, and this is F. If you look at the Visual Studio example. So it was F4, and this is just byte. If it is a 4 byte, we're going to extend the negative. So FF means 1, 1, 1, 1. So that means the number is still negative. You see, so this is 1 byte, 2 byte, 3 byte, and this is FF. So this is a 4 byte, 1, 2, 3, 4. So if you store this in the memory, like the way we did in Visual Studio, you're going to go right to left because it's Little-endian, right? So you're just going to say F4 first. If you want to go horizontal, I would go vertical. And then we're going to say FF, FF, and then FF. So these are 4 bytes, and that represent -12. Okay. So this is your skills in terms of binary and how to convert and how to do the 2's complement. It's going to make things way easier for you. And you already explained that you have to have a variable name, make sure that this is not a keyword, and you're going to decide what is the size. Is it a byte? Is it unsigned or unsigned? So this is a directive, this is the variable name, and this is the initializer. You must initialize it. So there is no way to say I cannot. So if you don't know what the value is, it's said it might not be 0, just use the question mark. Okay, so I already talked about this. So remember, this is unsigned byte. If I say it's signed, then you have to add the S byte. And we already talked about this example. So this is the word, it's unsigned, and this is a memory of size 4. And we saw that already in when I played with the Visual Studio. Okay, so these are the bytes. You can store a character right here as an ASCII, or store 0. That's the maximum. Why maximum? Because 2 to the power 8, it is going to be what? 256. So we're going to go from 0 to 255. So these are 256 things, right? So this is the maximum value. If you try to store 256, you might get an error. And if you notice right here, it's all unsigned, right? Unsigned. This is a signed number, and that is the minimum. You can think about it as maximum, but that's the minimum. So if it's 2 to the power 7, because we are taking 1 byte for the sign, so we're going to have what? 2 to the power 7, right? So we're going to have from -1 to -128, and from 0 to 127. So this is the negative domain, this is the positive domain. Okay, so this is the maximum value right here, or the minimum if you think about the -1 as the maximum value. All right, that's the positive one, that's the maximum. All right, this is the question mark if you don't really know what you're gonna do. Okay. So this is very important. So I would like you to do this example. Just say S byte. So this is unsigned, right? And assign it a negative value. See what happened. Is this gonna be acceptable or not? And if it's acceptable, why? I would like you to think about it. Okay, so if you declare S byte variable, the Microsoft Debugger will automatically display its value in a decimal with what? Leading sign, right? It does not prevent you from initializing byte with negative value, but it considered poor style. So try not to do this. This is a poor style. If you do this, there is a magic in there that's gonna say, I don't care about this. And if you have descriptive language, it's gonna, you know what I'm talking about when I say I don't care about the type, I care about the value. I don't believe the type, I believe the value. If there is a conflict, a negative number, but here they said unsigned, I don't believe the byte, I'm gonna go and believe what? Believe the sign, and convert this automatically in an S byte without letting you know. So they will do it at the runtime. They're not gonna change your .sm file, okay? So keep that in mind. So this is something that you can define an array of values. So you're gonna have, instead of byte less 1 byte 10, you can say comma 20, 30, and 40, and so on. So these are what we call arrays. So if you store this in the memory, you have less, and you have 10, 20, 30, 40. So the only thing you know, the address of 10. So how are you gonna access this? You don't have a variable name for this. So you have to go and say less plus 1, right? If you want to access this, plus 2. If you want to access this, you're going to plus 3. So this is plus 0. So you can also say less 1 plus 0, or you're going to say less 1. So these are both identical. Okay, and this is also a list. So in this list, you have a known value, and then you have 32, and then you have 41, and then you have this binary value. So you have a list, and this list in the memory is accessed with this variable. So the only thing we know here is 0, 0, because this is usually going to assign 0, 0. And then we have 32, and then we have 41, and then let's look at this number right here. So this is 0, 1, sorry, this is 1, 2, so in hexadecimal. So this is 2, and this is also what? 2, right? So this is 22. You can store them in binary if you want to, I don't mind that. So if you want to go to here, remember you have to say plus 1. We're going to talk about this in more details when we talk about memory access. Okay, so this is the string. We have been talking about integer. This is how you're gonna store a string. And remember, it often will be what? Terminated by a 0. That's the best way to do it. If you don't terminate it by a 0, we don't know. It's gonna be up to assembler to decide whether to stop reading or whether to add the .0 automatically. So keep that in mind, okay? I'm gonna show you this in Visual Studio maybe in the next class when I talk about it. So keep that in mind. These are like bytes, and these are gonna be terminated by 0. This is also correct, but this is used to be back in the days when they used to have memories declared, and they don't used to have this, like, that was impossible at that time to have it all in one quotation. So if you want to store this number, you're going to say enter, this string, I'm sorry, and then you're going to say n, and then you're going to say, t, and then you're going to say E, and then you're going to say R, and then you're going to say white space, and so on and so forth. It used to be very tedious. So that's when they come up with one quotation and they put everything. So everything right here is going to be stored in this way. Keep that in mind. It's going to be E first, and then N, sorry, and then T, and then E, R, and then white space, and then U, and then O, and then U, and then R, and so on and so forth. Okay, so it's going to be stored. So everything is a byte. So the only thing you have right here is a string R1 byte. You only know E. If you want to go to the second, +1, +1, +1, add 1 to from here. 0 + 1, going to take you here. 1 + 1, 2. 2 + 1, 3, and so on and so forth. That's what we call offsetting. We're going to talk about them later. Okay, so I think we have covered quite of the material so far. So let me stop right here, and then I'm going to continue later on the duplications, and we're going to continue from there. Okay, so I'm going to stop right here, and see you at the top of the office hours, and if you have any questions. All right, guys, thank you very much. See you later.